Hi everyone, welcome. My name is Somaya Sadat. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto. And it's my pleasure today to welcome you to this joint seminar with the University of Seoul in Korea. Our speaker today is Professor Shoshanna Saxe, who will talk about machine learning for understanding construction resource use and embodied greenhouse gases. Big problem, small data. Just a bit of introduction. Dr. Shoshanna Saxe is an associate professor in the University of Toronto's Department of Civil and Mineral Engineering and Canada Researcher Tier 2 in Sustainable Infrastructure. She is a distinguished international associate of the Royal Academy of Engineering in UK and sits on Waterfront's Toronto Capital Peer Review panel. She investigates the relationship between the infrastructure we build and the society we create to identify opportunities and pathways to better align infrastructure provision with sustainability. So with that introduction, I'd like to invite Professor Saxe to start her presentation.
Thank you very much. So as Somaya said, I run a research group at the University of Toronto where we research the intersection in between the physical world we build and the society we create, with a particular focus on aiming for long-term sustainability goals, particularly around greenhouse gas emissions and mitigating climate change. And I work on infrastructure because it's for me, the single most interesting thing I could spend my time on. But when it comes to society as a whole, or even a lot of academic efforts, infrastructure is perceived as something very in the background, right? We tend to take it very much for granted, especially in wealthy countries, that if we open our tap, the water will come out, that the transportation infrastructure will work, that our infrastructure will be safe and reliable, and we'll have a very high quality of service. This is from a comedy news show called Last Week Tonight in the United States. And they did an episode on infrastructure 8 years ago. And I really enjoy these fake quotes, right? Infrastructure, if anything exciting happens, we've done it wrong. Necessary, but yeah, it's something I've never thought about. And this manifests, of course, in how much data we have about infrastructure. We're not thinking about it that much. We're not measuring it that much. We're not paying that much attention, which I will get into later. But as I said, I think infrastructure is the most interesting thing that I could spend my time on. And one of the reasons that it's so interesting and deserves so much attention is that the infrastructure comes first. Infrastructure is a very strong predictor of how we live, how we move, who we meet, what we spend our time on. It's also a strong predictor of social values. And there's always this big question about, which comes first? Should we build the infrastructure to the behavior we see, or is it that behavior is manifested on infrastructure? And this is a great piece of research from Texas, from the University of Texas, where they looked at, which came first, the infrastructure or the behavior. And you see across examples, I've pulled two from the paper, that we had the infrastructure first. So we had track miles before we had trains, before we had people traveling on trains. And similarly for driving, we had oil pipelines before we had roads, before people owned cars, before people drove those cars. And that means that if the infrastructure is going to predict behavior, if it's, as I say, the skeletal structure for society, it's creating the world, and we have to take very seriously the infrastructure choices we make. So the research I'm going to talk about today is motivated by two major challenges related to infrastructure in the built environment. On one hand, around the world, in high-income countries and in low-income countries, we see massive infrastructure deficits. We see shortages in available housing. We see maintenance deficits, more need for more construction of more different types of transportation or water resource infrastructure. And that is going to consume a lot of materials and energy to build the amount of infrastructure we have planned. The general expectation is that over the next generation, over the next 25 years, we will build as much globally as have ever been built in history ever. So we will double the amount of built environment on the planet. On the other hand, we have the climate crisis, which demands reduction of consumption across all sectors of society. And so how do we build so much more while also polluting so much less? And if we look at that a little bit more in detail, These are some numbers from Canada. We have a growing population. Canada, of the high income countries, is one of the fastest growing, which is leading to demand for more and more housing. We also have a change in the size of housing that people generally expect. Houses in Canada have gotten 30% bigger since the 1990s and 100% bigger since the 1950s, both of which are meaning that to build more housing, and with more housing per person, not just more people overall, we have a lot more resource consumption. Canada as a whole is looking at needing to build about 5.5 million homes over the next decade to maintain affordability, just a massive amount of construction. And that's just talking about housing, not over even other buildings or other types of infrastructure. When we look at the impact of all of that construction, we're seeing already that resource consumption is causing more and more greenhouse gas emissions every year, both more in total and more in terms of share at a global scale. This is from the International Resource Panel, and they found that by 2015, almost a quarter of emissions were from resource use. It's probably closer to a third now that we're in 2023, and that is mostly driven by construction materials. Concrete and steel alone account for about 15–16% of annual greenhouse gas emissions every year. And that's due to the energy it takes to mine the raw materials out of the ground, to bring them to a factory, but also the chemical reactions that happen when you're processing raw materials into construction materials that are released to the atmosphere, which can't be solved just by using cleaner energy. So we have these two big problems. We want to both understand them, get a number scale of where we're headed, and try to do something to improve the problems in the future. And so we see in the literature a lot of efforts to try and address this using machine learning and big data. And so one of the most common ways to try and address this is using satellite data to categorize how much has been built where. And so this is not necessarily useful for predicting for the future, but can help us understand the scope of things like relationship in between level of development and quality of life and available infrastructure. And a lot of work has been done using satellite data or night lights data, where you can see the density of light in the space at night, which is heavily correlated with built environment, to come up with assessments of how much resource use or how much carbon, embodied carbon, has gone into building the existing world. And this data is really interesting. There's been a lot of really interesting techniques used, but it tends to be pretty high level because we can't get very fine-grained disaggregation with satellite data, that we're getting better at that. And it's pretty good at talking about where we are now, but not talking as much about where we can go in the future, which we're hoping will be different than the patterns we have now. And so this high-level data has led to advice that says, we need to change the pattern of construction that we're on, and some scales of the change that we need, but it hasn't been very good for coming up with advice that planners or engineers or designers can use to change how we build things, because it's tended to be very high scale. And given the scale of the problem, it's very appealing to want to use machine learning or other artificial intelligence type approaches to help solve the problem. And also people tend to recognize at least that the climate change problem is important and want to do something about it. And over my career, I've had many a meeting with ML or AI specialists who have many data analysis tools that they want to bring to bear to the problem. And the question that I get asked the most in those preliminary meetings is, what are your data analysis problems? We're really good at data analysis. How can we help you with that? And my main data analysis problem has always been, I don't have any data. Right? I know that there's a scale of a problem here. There are things we can do about it, but for the type of problems I want to solve, we just don't have data available. And so we have to either use a lot of proxies or do something in the future to solve that problem. And so when it comes to trying to represent at a more disaggregated scale and more detailed the built environments, the norm in my field has been what's called the typology approach. So if we want to know the resources used in every building around a city or in every bridge, it would be too effortful to go and categorize every single building one at a time. And so you put buildings into buckets. So maybe you made 15 buckets to represent the whole city. And then for each building, you come up with a representative building, either a real representative building or one made based on statistics or building codes. And you say, this building will represent all of the buildings of its type. And this approach, for instance, has been used by the International Resource Panel in this approach, where they use typical buildings in the United States to represent, with some tweaks, all built environment all over the world. And obviously, there are huge differences in between buildings in the United States and all buildings in the entire world. But it was a proxy that let the work move forward. And it was, in many ways, the best data available at the time. Another thing that is sort of the first place people go when they think we should be able to get better data for buildings and how they're built and what resources they use is people think of what's called building information models. And building information models are a 3D representation of a building. They're often made as part of the construction process. At some point, a building information model will be drawn. And they tend to look really good. They look a lot like buildings. It feels like all of the information that we need should be inside this 3D rendering. And increasingly, you hear talk of things like digital twins for buildings. And certainly I had the same instinct when I started doing this research. I thought, okay, we'll just collect a whole bunch of building information models and we'll have all of this really great data and we'll go from there and we'll be able to go back to the, what are your data analysis problems and not, I don't have any data. But building information models have tended to be developed for one of two main reasons. One, to make nice pictures to help have a visual representation of what the building will look like, or two, for clash detection, to make sure that when we're designing the building, we're not designing two parts running into each other in 3D space. That would be a problem, right? You don't want a structural column that you've built a duct through. And so they're generally not labeled in a detailed enough way that lets us know what's the resources inside. So it looks like a steel beam to the human eye, but it's not actually labeled as a steel beam in any way that a computer can use it. So we have these big problems, but generally there's been very little data available. And so starting, I guess, 5-6 years ago in my research group, we started working on the data problem and saying, okay, there's no version of the data we need out there to really understand how resources are being used in the construction of buildings and infrastructure. We're going to go develop it. And so what that meant was we started collecting drawings of buildings and other types of construction. And we have gotten the drawings from a range of places. Sometimes they're posted on public websites if there needs to be a commenting period before a permit can be issued. But most of the time, we've partnered with construction firms of some kind, from architecture firms or engineering firms or even builders, and they share with us confidentially copies of the construction drawings for real buildings that are being built. And then we go through them and categorize in very detailed as we can how much material is being used in what part of the building for what purpose, and then organize it all into a big database. And so what that looks like, for example, is here is a cross section. So we're looking at a building through the middle from the front. So you can see the ground and then the building standing above it. This is a 2-story small house, and trace the drawing. So for instance, highlight the wall, and then we can use the scale on the drawing to get the dimensions. And so we'll know how thick the wall is. And then if we use a drawing from another view, so in this case, this is a slice through the building looking down, and we can see the wall in pink, highlighted in pink going around, then we can know how much wall there is. And in a very crude level, if you multiply the width by the depth by the height, you get the volume of the wall. It's much more complicated than this because walls are not just one thing. They tend to have different layers like insulation and waterproofing and maybe something, drywall on the inside and cladding of some kind on the outside, but we go through it one by one. And then we classify all of the elements to a very detailed level of saying, what exactly is it doing in the building and what exactly type of material is it? And this has let us make a pretty big, for us, database of construction material use in buildings. And we've published it. And what it looks like is something like this. So what this drawing is showing is for every building that we've quantified, and there's about 112 buildings here, how much resource use is in each building, in this case, categorized by its high level categories like metals or thermal and moisture protection or finishes and wood, and then multiplied by the greenhouse gas intensity that it takes to make 1 unit of that product. And so one thing that this means is we have been working on this for 5 years, and we have come up with 112 data points. So for each one of these data points, it will take a member of my team between 50 and up to 200 and something hours to go from the plans to having a tracing of those plans, or drawing our own 3D model, working from the plans, and getting to the point of having everything in the database, which can be in Excel, but also can be in CSV or manipulated in Python. And we come up with quite good models, but this one, for instance, took 200 hours. And so if it takes 200 human hours to be able to make one data point, that's just a very slow process of accumulating data. And we have built, as far as we know, the largest such database in the world, but it's taken us, 5 years. And so if we wanted to get to 1,000 buildings at this rate, it would take us 50 years, which is, of course, still not very big data by many people's standards. But we were able to learn all kinds of things as we went. So we were able to look at, now that we have very detailed data, if we normalize it in different ways, what does that mean? Which becomes very important for how you should write regulation about sustainable resource construction, and also to get a sense of how much variation there is between buildings of the same type. So if you remember, I said that one of the very common ways to do it is to use a typology where you represent an entire class of buildings by one type. So one of the things that we checked was, well, how much variation would that be that's not captured by using that single representation? And what we found is that depending on how you normalize, it can be quite large, but at a very baseline, we see at least 15% spread around what you might say is a typical number, but that also all kinds of other things came out of that research. So here we looked at how much variation is there in resource consumption between big houses and small houses, and that have very similar functions and very similar purposes, but might just be bigger. And we saw resource change and embodied carbon changes up to 300%. And we also tried normalizing per bedroom, which is the bottom graph. And we found that for normalizing per bedroom was a much better representation of overall impact on the environment than normalizing per meter squared. And this is advice that we've been able to take to planners and builders and help try and put into regulation, so that we come up with guidance around embodied carbon and resource use in construction that is more likely to reduce overall pollution. Other things we were able to pick up as we were going and making all of this data is, while there has generally been a story that the taller buildings get, the more polluting they get, what we found is that that's really not necessarily true. And there's a huge amount of spread, that there are less polluting tall buildings and more polluting tall buildings. And you can see here, there's one 50-story building with much lower embodied carbon than many much shorter buildings on a per bedroom basis. And so what we found is that it's much more about the design of the individual building than it is about any particular class of building being good or bad. And because we had classified the materials in so much detail, we knew where in the building they were and what they were doing, there were a bunch of things that we could start checking, like what about above ground versus below ground? And what we found is that the buildings that we were studying are really icebergs. And so for some very tall buildings with big basements, we would see a lot of resource use and a lot of embodied carbon associated pollution, whereas a very similar building with the same number of units and the same number of bedrooms, if it had a small basement, would have much less pollution. And so this was one of the number one things that we found as we were creating this data in this very detailed way, was that it was the underground construction was the biggest driver of single biggest driver of building related pollution. And that what we needed to be doing was avoiding underground construction, which in tall buildings means avoiding underground parking, or generally avoiding parking in general. And for lower buildings meant about not building, rec rooms or granny suites in the basement, but concentrating as much as possible of our living space above ground. So these were all things that we found by going through the data, and we've published, I think, 3 or 4 papers using this already, with more coming, so that we're both getting products out of the work as we go through the research and also sharing what we're learning. But this approach of creating buildings, 200, 250 hours at a time is painful and slow. And it's very appealing to think, well, can we use other techniques? Can we use the modern machine learning and artificial intelligence to do this faster and better while still maintaining the disaggregated approach? So we started saying, okay, well, let's go where the data is. And when it comes to the built environment, one of the biggest, easiest pieces of data sets available are things based on images. So in this case, we've been done a lot with Street View. You can also use aerial view images, but Google Street View is widely available from a huge number of cities and places on the planet, almost everywhere where you have big concentrations of development in the global north. So could we rely on that? And one of the first things we wanted to check was just, could we get the data? Could we isolate and get pictures of the buildings? And could we use it to predict something that you should be able to see with the human eye? So our first effort was we looked at height. And so the city of Toronto, where we did the research, publishes general shapes for more than 400,000 buildings in the city. And combining this with Google Street View, we could identify both where the building is, where we might have a clear view from the street to the building, and take pictures of it. And so you can see for the red building highlighted here, you would have clear views to one face from the street running up and down in the middle, but for the other side of the building, it would be blocked by this blue building, and you wouldn't be able to get a clear picture. So we'd only be able to see part of the building. So we created a convolutional neural network using transfer learning to see, once we could feed in a photo of the building, could we get an idea of how tall it was? And the general results were that we could do a pretty good job with height. The average error was about 0.5 meters, both for short buildings and for tall buildings. And it was very nicely concentrated around the mean. And so we were pretty satisfied with that. And we also saw that the model was doing things that we thought seemed reasonable, like separating out what the sky was from the greenery, which felt like it would be a reasonable thing if you were trying to predict what height was. And other people have used other approaches of using pictures to try and predict things about the building. So in this piece of work from the UK, they created their own mobile image and data collection, basically a car that would drive around and would take pictures of buildings from the front. And they used it and computer vision to identify elements in the building, like windows. Could you tell how big the windows were and identify where the windows are? And this work is really great and very helpful if you, for instance, want to know how much glass there is or what windows might be available in the future if you demolish a building, or how much glass you should be trying to recover in a window shape. But with both the work that we were doing and this work done by others and other papers, you're very limited to what you can see from the street. And so if, for instance, like with the red building, you're only going to be able to see part of the building from the street, then there's a huge amount about the building that you're just going to miss if you're using photographs. Similarly, any part of the building that's underground, you're not going to be able to see in any picture because it's not visible to the human eye, it's underground. And so we've since moved on to, well, can we predict things that you can't see with the human eye or taking pictures? Because the picture itself would give us enough proxy information that would tell us something about the building. And so we've started with size. We're also working on age at the same time, because when we're interested in resource use in a building, knowing what era it was built in can help us tell how it was built. And so if we, for instance, combined a good idea of how big buildings were with the knowledge we have about how much resources are used per meter squared, we could get reasonably good pieces of information. And so just some numbers to hold in mind, right? There are 400,000 buildings in Toronto, and that's the scale of prediction we're trying to get to. So even if we had 100% data, we would only have 400,000 data points. So we're never going to be able to get up for the city of Toronto to millions of data points, because there just aren't that many buildings. If we wanted to do it in something less common than buildings like bridges, we'd be talking about 320 data points in the city of Toronto. For roads, similarly, there aren't that many different roads when we're compared to big data, which is often measured, in the millions. When we're talking about the built environment, there's just much less of it than that. And so for the image prediction, we've been looking at using a structure based on ResNet. And a lot of our early challenges were about the model overfitting, because we just didn't have as much data as the models were expecting. Dealt with that somewhat by freezing some of the layers and trying to make the models smaller, and also working to increase the amount of data that we're feeding into the system. And so this work is very much ongoing. And so you can see some results on the top of how we were able to do in terms of accuracy with our first set of data, which was using 16,500 photographs of different buildings in Toronto. We've since upgraded to 46,000 photos. We thought it might be possible that using more data would help with some of the accuracy. And we saw, a 1% improvement. So we think we're probably maxing out on what we can get in terms of more data giving us more accuracy. And we're accurate to, about 24%, 25% accuracy. So we were hoping to eventually push that down below 20%, but maybe it is good enough, especially for something that you can do from a much easier available data set than trying to go through buildings one at a time. Similarly, for age, we're looking at accuracy in about the same ballpark of categorizing the buildings in Toronto into 3 big buckets. It's in pre-World War II from 1940 to 1980, which is mostly post-World War II, and more modern buildings from 1980 through 2020. But there are a bunch of challenges that we haven't totally wrestled with the and I'm not sure we're going to be able to, with the way that buildings are built, which makes it hard to do things from images. So one, we like to build buildings in what's called a revival style. There have been a lot of instances where we build modern buildings in the style of old buildings because that's the way we like them. And so we can see in this case, in the picture in the top left, is a totally modern building, but it was built to look like it was built in the late 19th century. But it's not. And from a code standpoint and internal materials, it would be completely modern. But it might be hard for both an untrained human, or just the average person, or a machine learning model to learn the difference in between a building that was built in the 1900s and has been washed, and a modern building that's shiny but is modern. Another thing that happens is we have what's called facadism, where you tear down the entire building, but you keep the front face, you keep the facade. And this happens a lot, especially in North America, where we like the look of old buildings, but we don't really want to use them anymore. And we have heritage protection laws that protect the way it looks to the street, but not the rest of the building. And so you have things where the front of the building looks old, but actually everything inside is totally modern. And so you'd have a similar type of challenge that you had with modern buildings built to look old. You can also have a question of everything becomes a bit of a mishmash, whereas different parts of the building will be replaced at different times. So an old building might have completely modern windows, and maybe that will be something that the ML training would pick up on that would get confusing, because we're telling it it's a really old building, but parts of what it's seeing are very, very modern. Another thing is that buildings get extended in the back. So this picture on the bottom left is a picture of an extension, whereas based on what the building looks like from the front, you could expect that there are many buildings like that that are all kind of the same size, so they're built in the same time period on the same blueprint. But just like different parts of building get renovated at different times, over time, building volumes tend to expand backwards, which we wouldn't see at all from the front. Another challenge is that the data is very uneven. So this is an old map, but it shows in the city of Toronto when different parts of the city were originally built out. And so in orange and brown, you see the parts of the city that were predominantly built in the pre-war period. And then in blue and green, you see pushing out areas that were built very rapidly in the 1970s, 80s, and 90s. And it means that there's a huge number of buildings, especially of homes in Toronto, that were built in the 70s and 80s when Toronto was going through a really rapid construction boom, and fewer that were built before then. And then there's also a spatial relationship, as buildings that were built near each other tended to be built at the same time. And then since 2000 or even the 1990s, when Toronto was fully built out, you get replacement of buildings, mostly since then, some torn down, but some partially renovated in some of the ways they made before. So these are all things that confuse the task and may make it harder to do, or may not even necessarily make it completely solvable to a very high level of accuracy. So before I go to questions, so what do I think was the whole point of this? For built environment problems, which I would argue are really important ones, because to get the built environment right is foundational to how our society functions. We're not living in a big data environment. Even if we had full data on every building we built in a city, that would not be reaching the scale of millions. And we just don't have that kind of data because it's not historically been something we paid very much attention to. Which means that if we want data on these types of problems, we're going to have to make it the slow, hard way. And that means it's something that we have to value and put time in and figure out a way to reward people for doing. Because, for instance, if we couldn't have published all those papers on the way, we would not have been able to keep doing the research that's creating the data and making the data set bigger over time. And then there also becomes a big question of how much accuracy is necessary to be useful. The current ways of doing things, I think, are at least 15% off. Does that matter? I think sometimes it matters, because when we're looking at greenhouse gas mitigation strategies that can make a 5 or 10% difference, then if the data is more uncertain than the potential intervention, it might be hard to judge if we're talking about a really effective change. But if we're already 15% uncertain and we're going towards something that might be easier or faster, but it's 25% uncertain, where's the trade-off in between speed and accuracy, and do we care, and are the machine learning tools going to be good enough? I don't know what the answers are to the questions, but we're still working on all of these things, both the data creation, the prediction, and trying to learn as much as we can about how to build more with less. And I would be happy to take any questions.
Thanks a lot. This was very interesting. I invite everyone to type their questions, please, in the Q&A box you see on your screens. Maybe I'll start just by asking, who would use this research directly? Is that the municipalities, perhaps?
So I think it depends a little bit. I mean, I find it kind of hard to imagine a municipality running an ML model like this on their own, but the types of questions I'm hoping to use it for are to understand better the ways in which different urban forms influence resource use. And if I could process that really quickly or faster, that would be helpful. I mean, I think this research project is going to take 10 years before I start getting to the results I want.
I see.
And 8 years in total from start to finish. And if we could have done it faster, then we would have had results faster to give advice faster. Also, you could imagine, I mean, one of the classic examples of understanding what things are made of are, you could understand, there's the idea of treating the built environment as a potential resource source. And so for urban mining, or for recycling or for demolition, it could be interesting for those standpoints. I'm very interested in thinking about what do existing neighborhoods tell us about how we should build in the future, but a lot of people are interested in urban recycling.
Thank you. I think we have 2 questions in the Q&A box. And could you also read them out? Because I think our participants don't see the questions.
Yeah, okay. So they might see them because of the way my screen is working. I'm gonna stop sharing. So the first question was, what was special about the 50-story outlier building you mentioned that had lower embodied carbon than single unit houses? So there are a couple of things. One of the biggest ones is not having very many basements. So if it really limits the underground construction, then it will have not very many basements. Another one is in terms of having effective layout in terms of design. So it gets a lot of bedrooms into its available space. And another big one is just having rationalized shapes. Box shapes buildings tend to use a lot less materials than ones that look like wedding cakes because of load transfer. Okay, so sorry if I missed this, but is the higher intensity of emissions for below ground construction because it uses more concrete? So it's not necessarily that because it uses more concrete, though that is the way it manifests, it's because it uses more structure. When you're holding, a building has to hold up the loads on it. And so when you're above ground, the things leaning on from the side are air and wind, to be very simplistic. And if you're below ground, what's leaning on the side of your structure is water and soil. Water and soil weigh a lot. You also have to make sure the water doesn't come in. And so you just need a lot more structure underground than you do above ground, or to hold back the loads, which are higher. And because it's underground, you need it to be waterproof, we tend to use concrete, so we tend to use a lot of a very heavy material. Is there scope to expand the data set more broadly to other similar cities in North America, or is the data very regionally driven due to region-specific zoning practices, etc.? Okay, so in our database, we do have buildings from other places, mostly because we needed people to share data with us. And so it was not a random sample of data by any means. It was who could we convince to share construction drawings with us, or rather, it was who could I convince to share construction drawings with me. And it's a lot of that is in Toronto, but a bunch of it is not. So we've got buildings from Ottawa, from Vancouver, from places in the United States. And sometimes things are very similar, and sometimes they're quite different. In California, where there are high earthquake standards, you would expect to see some pretty big differences in the way tall buildings are structured so that they don't fall down in an earthquake, which we don't have to do in non-earthquake zones. We've also done a bunch of research, which I didn't show, about how do smaller buildings change between different places. And so my PhD student, Aldrich Garcia, published a paper earlier this year looking at what's the difference in resource use in houses in Toronto in Canada, and Perth, Australia, and in Luzon in the Philippines. And we found that the differences are really big, that the style of how buildings are made, the materials that they're built out of, makes a pretty big difference. And so we have to be careful with regional transferring because there are lots of different ways to build a building. So for instance, Luzon, almost everything is made out of concrete block. In Perth, all the buildings were structurally brick, whereas in Toronto, we have stick framed buildings with brick cladding as pretty dominant. And what makes each building more or less sustainable varies a lot. So the buildings in the Philippines, for instance, use much more materials on a per meter square basis. But in Toronto, our houses are so much bigger that we used way more materials overall. Okay. And then how do you foresee using this research project to mitigate GHG emissions in the future from a practical perspective? This seems to me more like an exercise of collecting data on how buildings have been built to date. Can you give some concrete examples of how construction engineers, architects, etc., can use the results in the research and practice? Okay, so I like the bluntness of the question. Almost everything we're going to build in the next decade, we're going to build with existing tools and knowledge. There is no time to translate new anything inventions out into real practice. Everything that's hasn't made it out yet won't make it out in the next decade. That's just, things change too slowly in the construction sector. And so that means if we want to do better in the near to medium term, we have to do it with construction tools and knowledge that we already have. And so understanding, for instance, what does a best-in-class building look like right now? Where are the hot spots of emissions within a building as ways to do better? And so advice that we've come up with already, that we've given a lot of people, which I don't know, may sound obvious to this person who asked the question, but have certainly generally not received as obvious in practice, is the importance of underground construction as being just a huge suck of materials and greenhouse gas emissions, and rationalization of function. So it's very common to say, as I mentioned, let's make the building better per meter squared, but that doesn't necessarily make the building better. It could make it worse overall, because that's a very hackable metric. And so I could go on, but understanding what are the best in class buildings and where the hotspots are is, I think, for us and for the advice we give, helping to guide towards better buildings that can be done now, that don't have to wait for something new to get out of the lab into practice. All right, no more open questions.
Anyone else? Going once, twice? Okay, great. I think this was a really interesting seminar for me, at least, and I'm sure for everyone who joined us today. I'd like to thank, there is one more question.
So does a building's ongoing emissions energy usage factor significantly into buildings' lifetime emissions? The answer to that question is it depends. So depending on where the building is and how it's built, if the building is in a place where electricity is generated by coal and it's running a lot of cooling emissions, then the operational energy is going to dominate the lifetime emissions, and it's a really, really big deal. In a place like Toronto, where our electricity system is pretty clean, then depending on how insulated the building is, you can see, more like 50-60% of the emissions being about the upfront construction as opposed to the operation. There's a bunch of things that come into answering this question. Like, for one, what do you assume about the energy system 20 years from now when the building is calling on energy? Two, how long do you think the building is going to last for? And so what do you mean by lifetime? Oftentimes people mean 60 years. In some places, buildings live much longer than that. In many places, they live much shorter than that. Other things that can matter is also, do you care about something that's happening in 2060, and how do you weight that towards emissions that are happening in 2025? What discount factor do you apply to your emissions? So there isn't one right answer to that question. Increasingly, we're seeing that the upfront emissions are more important than the operational emissions, as we've both gotten better at designing energy efficient buildings and our energy networks are getting cleaner. And also at a global annual scale, the construction material emissions are getting more and more every year. Okay, so what is the reason that underground construction is more GHG emitting? So as I mentioned before, it's because underground loads are higher, and so you need more structure.
Okay. I think that's about it in terms of the questions. Thanks again for the great presentation today, and thank you everyone for joining us tonight. On behalf of ourselves at the University of Toronto and our colleagues at the University of Seoul to attend this seminar. Thanks a lot, and have a great day or night, depending on if you're in Canada or Korea or elsewhere. Thanks, and have a great.
Thank you for having me.
Thank you.